Welcome to the video on geometry. Now, don't freak out. This is not like geometry in math class. We're not doing any math here. We're just talking about the shapes of the atoms. Let's talk first about why the atoms have their shapes. It all has to do with their electron pairs. So we know that electrons are negative, and all the electrons are negative, and the electrons are on the outside of the atom, and so all of those negatives are repelling all the other negatives because two like charges repel. And so this is called VSEPR, which stands for valence shell electron pair repulsion theory. Meaning that if I have an atom, let's say this is my atom, and this is my electron cloud around my atom. If I was going to bond this atom to another atom, those electron clouds are going to repel each other and try to be as far away from each other as possible. Now the molecule is still bonded together because it's touching, but the electron lone pairs of the atom are as far away as they can get. So if you have two atoms trying to make a bond, they will wind up in this 180-degree fashion. If you add in a third atom to our molecule, that will repel both of the original two atoms, so they're no longer going to be in a 180-degree fashion. Now they're going to repel each other into 120 degrees apiece. And if you add a fourth molecule to this, it's going to push them away again, and now it's going to take up a three-dimensional figure, and that's going to be something called tetrahedral. We'll talk about that in a minute. So the point is that these electrons are repelling each other, and because they're doing that, the atoms are forming a specific shape in three-dimensional space. So let's talk about what those shapes are. You are going to need to memorize this table. The way we figure out, without having to blow up a bunch of balloons every time, what shape the molecule is going to be is we can draw it out and look at how many bonding partners and how many lone pairs the central atom has. Let me write that down. This is all about the central atom. Now, the simplest kind of molecule is a diatomic molecule, meaning it only has two atoms involved. Because there are only two atoms, there really is no center, but we know from geometry that any 2 points make a line. So these are going to be linear, with those electron clouds as far away from each other as they can get while still being bonded. So we have no the lone pairs are not really relevant. Yeah, there are 3 lone pairs in each of these fluorines, but it has nothing to do with that. It's just because it's 2 atoms. So there's only one bonding partner for each of them, and we call that linear. All right, the next type of molecule is a molecule that's made of 3 atoms, triatomic, and the central atom is therefore bonded to 2 atoms, and that looks like this, where the carbon is the black one and the oxygens are in red, and there's double bonds there. Now again, I'm not concerning myself with the lone pairs on the oxygen, of which there's 2 apiece. We're looking at the lone pairs in the central atom. There are no lone pairs on the carbon. So here's carbon, no lone pairs, 2 bonding partners. This is also linear because it's in a straight line, with those oxygens being as far away from each other as they can get. Then something interesting happens. Once you start having lone pairs on the central atom, you get something like this, which is water. Again, the oxygen is red, hydrogens are in white, and instead of being linear with the 2 hydrogens as far away from each other as they can get, these lone pairs on the oxygen, which are also negative, push those hydrogens out of the way and create something called bend. Basically, it's bending the hydrogens down. And so this happens when you have 2 bonding partners and 2 lone pairs. You can also get this if you have 2 bonding partners and 1 lone pair. And in that case, you have a double bond thing going on there. The next kind of atom is when you have 3 bonding partners and no lone pairs. And you might notice that this is an exception to the octet. This boron is not happy, but that's the way it goes sometimes. And that, you have no lone pairs, 3 bonding partners, you are called trigonal planar. Tri meaning 3, so it's got 3 bonding partners. So trigonal like a triangle, but it is planar because if you look at it from this point of view, all the atoms are lying in a plane. See, there's your geometry coming into play. Well, just names. All right, next. What if we take our trigonal planar and stick a lone pair on that central atom so that it's happy? Well, that lone pair, again, is going to repulse those hydrogens down, away, so therefore it's no longer in the same plane, and it kind of looks like a pyramid. So we call this pyramidal. Pyramidal means 3 bonding partners, 1 lone pair. Now what if we take that lone pair and replace it with another atom? So it's going to be essentially in the same orientation, but now it's called tetrahedral. Tetra meaning 4. So you have 4, no lone pairs this time on that central atom of carbon, and that's tetrahedral. And then the last one is another exception to the octet that we were drawing in last class. This one has 5 bonding partners, no lone pairs, and so it looks like this. Kind of reminds me of a space station, actually. But it looks like this, and this is called trigonal bipyramidal. I'm going to write that down, I'll show you. Trigonal bipyramidal. 5 bonding partners, no lone pairs. Where do they get this name from? Well, trigonal stands for the middle 3, or the equatorial atoms. So there's 3 atoms here around the middle, and then the bipyramidal, bi means 2, it's 2 pyramids. So if you take a look at the top, there's a pyramid there. If you take a look at the bottom, there's like an upside down pyramid there. So that's trigonal bipyramidal. You need to be able to give me the name of the shape of the molecule based on how many lone pairs and how many bonding partners it has. How are you going to figure out how many lone pairs and bonding partners it has? You have to draw it. So this unit is very cumulative. So we started off with the naming. You have to be able to name things so you can write the formula for them. Once you get the formula, you have to be able to draw it. Once you get the drawing, you have to be able to figure out what shape it is. Now there's only one more thing I need to say about shapes, and that is there's 2 kinds of geometry. This right here is called molecular geometry. What is the shape of the molecule going to look like? And you can see that when the molecule has more bonding partners versus lone pairs, you get a different shape. There's another thing called the electronic geometry. And in the electronic geometry, electron lone pairs are considered the same as an atom, a bonding partner. And that simplifies this table because look here. In this case, we have this one, and this one. They all have 4 somethings. They all have either 2 bonding partners, 2 lone pairs, or 3 bonding partners, 1 lone pair, 4 bonding partners, no lone pair, total of 4. So all 3 of these are called tetrahedral in terms of their electronic geometry, because they all have 4 something on the central atom. So that kind of simplifies the table because you only have linear, tetrahedral, trigonal planar, and trigonal bipyramidal as far as your electron configurations are concerned, as far as how many total electrons or bonding partners. They call those domains of negativity. Because electron lone pairs are negative, and bonding partners are surrounded by electron clouds, those are also negative. So those are called domains of negativity. And so there are 2 different kinds of geometries. I'm going to focus primarily on the molecular geometry, but on the STAR test, they said that they want you to know the electronic geometry, so I'm just going to throw that out there too.